Hey.
Hi, how are you?
I'm good. How are you?
All right. Well, Jesse?
Okay. Can hear things now. Yeah. Hi. How's everyone today?
All right. Yeah, good.
Good. I didn't prepare any Notion page or Google Doc or anything. I figured we could just do what we did last night and pull up the paper and go through it.
Yeah. I'm just setting that up. Like the last time. Okay. I'm actually almost there. So yeah, I think we basically got up to section 2. It's not letting me log in. Here we are. Princes of the Universe. So I think we got all the way to here, and I don't know if we had any lingering thoughts or we just want to go into here. I know we were talking a little bit about the paper, and this is one of the things that's sort of being put forward in it. We argue that in most systems not explicitly driven by imperatives of an organism or computational agent, teleology is an illusory aspect of feedback given good regulation, or as an outcome of reciprocal causality. And that's kind of a commentary on the sentient stuff.
Yeah.
So that's one of the points that we had. Anything you want to say with that? But we're at part 2, and we'll go from there. Toy models and challenging idealized good regulation. We will give 2 examples of how EGRT representation of a constrained world along with pros and cons. 2 examples of how an EGRT with a representation of a constrained world. Is this sentence right? 2 examples of how blank of a constrained world. Okay.
Like, yeah, well, it should be ever good regulator, but yeah.
Okay.
Yeah, it's like, it's like you say EGRT and then it's kind of like automatic, but really it's ever good regulator. So that's what it should be.
Yeah, sure. Okay. Collectively, our toy models provide challenges of the idealized this thing in the last section. Excuse me. The first toy model is a sand pile avalanche model which is representative of a memoryless Markovian worldview. By contrast, alternating procedural acquisition toy model represents the non-Markovian memory-dependent system. This provides context in how these models can and cannot learn and be used in the context of prediction. So the first one is the sand pile. And diffusive processes challenge good regulation. So one way to test the notion of good regulation is to challenge it with a model of stochastic non-uniform processing. We demonstrate this with a toy model based on the sand pile model of avalanches to see how good regulator deals with burstiness and unpredictability. A series of avalanches can be embedded in a stochastic time series shown as in figure 3. We demonstrate, I don't think we can see that yet. We'll get to that after this. We demonstrate in a case in which maintaining a good regulation translates into identifying precursors of self-organized criticality avalanche triggers. Observing criticality using the sand pile model has connections to non-equilibrium thermodynamics, diffusive processes, and non-Gaussian systems. And in short, optimizing our model through error minimization is not, consistent with a process that changes with the instance of observation. An autoregressive fractionality or fractionally integrated moving average, our FEMA model, in a model with suitable predictive capacity. Our FEMA pre-filters the data to make input from the world stationary as well as generating static and dynamic forecasts, which represent both future versions of both present and future versions of the world representation. Each dynamic forecast is integrated with the present model, providing a means for prediction. This assumes the given model observes a complete world. The world is different for each observed instance, requiring an exhaustive number of observations to build a world model. Contemporary LLMs are typically autoregressive in nature. They're slow, based similar to understanding avalanche models using autoregression. Autoregressive based LLMs are slow, similar to how understanding avalanche models using autoregression is incomplete. We can look at diffusion-based language models to increase performance under a wide range of tasks, suggesting there is a fundamental law of good regulation at work here. Furthermore, pre-filtering techniques, stationary assumptions, can limit predictive aspects of the model since avalanches produce structure in multiple timescales. So let's see if we can find, is this figure 3? I don't know if it is.
Maybe, go down to the legend. Go down further. Yeah, that's figure 3, yeah.
Okay. I don't know if this came over well in this document.
Yeah, pretty well. I mean, it's a long figure, but it's got like different panels. A shows the avalanches, B shows like the feed forward, C shows the feedback.
I don't know if we want to look at it or just read the caption here, but okay.
Sorry, what's the figure supposed to show?
So it's supposed to demonstrate the avalanche model. The A is like the basic avalanche for 2 different parameters. Then B is the, let's see, feed forward component. C is the feedback component. Can you scroll up on the legend a little bit?
Yeah.
There we go.
Like,
yeah,
okay.
Yeah, right there. It's good. And then 2 means of modeling it. So B is a feed forward component. C is the feedback component. So showing like kind of the next time step and the previous time step throughout the simulation. And then D are 2 means of modeling an avalanche. So there's this aspect. It's mentioned in the appendix, but it's like a threshold model and like showing the activity at multiple scales. So like, for the entire system and for a little chunk of 100 time points in the inset. And then that's D. And then this second part here, okay, yeah, that's the top, bottom, and then E through I, which is down here, these images of W. Ross Ashby, are these sort of, let's see, image of W. Ross Ashby progressively embedded in random noise, and then progressively sharper power noise at the bottom. So this is basically a diffusion model of image processing using the avalanche. So the top is kind of like a non-avalanche, and then the bottom is an avalanche. So it's basically introducing this 1 over F noise instead of using a Gaussian to sort of do this forward diffusion process, which is explained in the abstract. Basically how diffusion works is you have a set of training images, you embed them in some noise, you train the model on it, and then it's supposed to recover the image from the noise. So it's kind of like it uses the noise as a way to introduce variation into the image. So if I show you a picture of a car with no noise, you can recognize a car. But if I mask it with noise, you might not be able to recognize it as a car. And if you introduce enough instances of different cars with a lot of noise, it forces the model to sort of pick out certain features and other things, and just it should reconstruct. And so there's been a lot of work on diffusion models, where they've done this. So the methods are in another paper, but I just did a simulation of a forward process of diffusion just to demonstrate what that looks like.
Okay, that makes sense.
Yeah.
Thank you.
You're welcome. Yeah. So I know it's a big figure, but like it's again, I think it's a constraint of the venue. It's like, yeah.
We're here. The sandpile and diffusion model examples in the figure allow us to consider non-programmatic features of complex systems, and how cybernetic regulation can assist in building robust world models of such systems. This requires small corrections to be added or subtracted from the main center of gravity. We can use ensemble averages to characterize the normativity of avalanche behavior over time. Descriptive parameters include average relaxation time and the average number of collapses per sand pile. This continual incremental state breaks down when the global state undergoes first order phase transition. Has designed et al. Explore outcomes of stochastic gradient descent for generalized non-convex problems at a distribution. A gradient descent process based on Boltzmann-Gibbs distribution visits critical regions much more often than other regions of the problem space. The nature of stochastic processes, such as diffusion, provide a means for good regulation of a hard computational problem, such as predicting avalanches. These are also analogous to aha experiences, where sudden insights lead to problem-solving success. The link between memory capacity and stationarity is related to differencing. Under stationarity, differencing between two adjacent datum is lossless. As the system becomes non-stationarity, the differencing operation is lossy, with a greater loss of information as the degree of stationarity increases. Unpredictable shifts in control might also be analogous to making an emergency stop when driving a bike. The detection of this occurrence not only disrupts good regulation, but it in fact cannot be fully prepared for. Anything on 2.1, the sandpile model, we want to discuss? Questions?
No, yeah, probably check it over a little bit to make sure that it's all sort of, consistent, or, because you can read it now, but like, have to think about like whether it make sure it's consistent. But that's okay. It's just.
Yeah, it's good.
I think it flows though. I think it basically flows together.
Okay, it's just a blank page, I guess. Let's see, Taylor Swift one. Alternating procedural acquisition challenges good regulation. Another way to test the notion of good regulation is to challenge procedural learning within alternating environmental baselines. We introduce a potential model of good regulation based on reducing task conditions in an alternating fashion. A paradigm for alternating between different conditions is introduced, allowing procedural learning through differentiable aspects of mechanical environment. The full extent of this environment is approximated via changes to and removal of force fields in sequence. The regulator solves an inverse problem and produces continuous behavioral output. Through um, through memory consolidation, the model of motor behavior becomes tightly mapped to the mechanical environment through memory consolidation. And EuroPS Mayo Challenge winner used two phases, learning, relearning, to achieve alternating procedural learning. Counterclockwise rotations were followed by mixing clockwise and lack of rotations. Increasing variation in the second phase forces the learning model to engage in inference. Learning, unlearning, relearning allows us to build counterfactuals into a model distinct from the training set. From this, a world model results that expands the latent spaces to unexperienced phenomena. As to criticality, the controller is faced with a challenge to the history of the system, but this time at regular intervals. 1 second. Okay. Yeah, so it's an interesting juxtaposition to the earlier unexpected bike stop, emergency stopping one. The procedural learning example, figure 4, involves embedding different force fields, rotational regimes in a time series. R encounters an alternating series of rotational regimes and must include the differences between the force fields in the role model for motor control. As the model for sensory motor adaptation, regulated behavior is the product of closed loop feedback systems. Transitions between alternating regimes are discontinuous and are not easily predicted by a regulator without reference to a global behavioral space. However, alternating procedural learning produces dynamical movement behavior that is composed of environmentally appropriate alternative outputs. Alternating procedural learning produces in the spirit.
What does that mean? I know there's a citation, but
let's see. Alternating learn. Just meaning that when you change the stimulus, both of the conditions are sort of alternative forms of the environment, I guess. So it's like if you have different rotational forces, there are different things that can occur in the environment that you don't experience all at once. So you just kind of expand your range of things that you're experiencing. So I might experience rotational forces to the right, and I don't experience any rotational forces to the left. Well, I can't learn the ones to the left unless I do this alternating procedure where I can compare right and left and that sort of thing. But it probably should be rewritten. I'm looking at it now.
It was mostly environmentally appropriate alternative outputs. I wasn't sure what environmentally appropriate means.
Yeah, no. It's hard to say. Yeah. So probably some other set of words there.
Okay, in the spirit of more conventional ML benchmark tests, alternating procedural learning also provides a means to learn color spectra, in particular gradations between color values in a CMYK color space. I feel like I'm missing something here. Figure 4.
Figure 4 is probably down further.
Is this?
That's part of. I think that's part of the. It looks like it's part of the legend for Figure 3, actually.
Oh.
Yeah. So go up. Well,
Okay.
yeah, wherever
Yeah.
you were, because it looks like it extracted figure 3 twice, maybe.
It might have, and I might have just. I hope I didn't delete anything. I'm worried there's something before part 3 that I deleted, basically. But
I'm not sure. But go up above the figure again. Where are we with? So we have the 3, but like, where do we go up?
well, basically, this was the end, the scene with color space, and then this is figure 3.
Well, figure 4. That may be. Well, yeah, because that's kind of like the next figure down there. So I think that was the end of 2. Yeah. And then, so this figure 4, go down a little bit.
Yeah, you do that, and I'll try to pull up the actual paper to make sure I'm not missing anything.
This is just showing this sort of learning, unlearning, relearning. It shows it in the force field form, where you're learning alternate types of forces, and that's kind of in this procedural learning paradigm. But then you can also do things like learn the sequence of colors in a color space by introducing certain combinations, disrupting those combinations and then putting them back together. So that's what that figure is. And it's just making the comparison for those 2 cases. And and then I think the color space example is in Appendix D more. It's discussed a little bit there. So those are all there. But yeah, then it goes into. I'm pretty sure it goes then from there into section 3. But
I guess we can comment on this. Well, I don't know. Do you have a preference between looking at the PDF outright or this? I mean, it's easier to see one or the other.
Well, you can make comments in this, but
yeah. Okay, we'll go here. So we're up to part 3, and I did check. Like, there wasn't anything back. We didn't really miss anything here. This is just a big figure kind of thing. So part 3, world models and generalized intelligent behaviors. World models can act as good regulators. So with good regulation, generalization is the achievable goal rather than an intelligence that can be optimized in any single form. So generalization, yeah. When evolution provides an abundance of intelligence behavior examples for a while, there is no universal notion of intelligent behavior. By contrast, the good regulator has the potential to provide a universal mechanism for intelligence generalization. Okay. Under the right model, the regulator can match the system under both equilibrium and non-equilibrium conditions. The point of the sandpile and alternating procedural learning examples is to indicate how much more we need to build a world model from a good regulator. Well,
put an emoji in.
This looks crazy, but sure. It's easier than I can't really highlight it the way I want to.
Yeah, I know. It's that's actually fun. I think that's like a nice new thing.
Put faces there.
Yeah. You don't want to get too many surprised or shocked faces or poop emojis. That's the goal.
Yeah, we'll use our basal affectivity, valence, and magnitude as paper review metrics.
Yeah.
So I think this is all thinking. Yeah. Okay. Right. So for EGRT to have utility for AI applications, we must recast the qualitative terms of cybernetic regulation. So poor regulation, or more specifically mismatched regulation, might be implicated in negative hallucinations, like breakdown, false memories, pathology, lack of incorporation, and positive creativity, referential loops moving outside of the test referential loops, adapting, redundancy, etc. attributes. So we're moving beyond good or bad here.
Right.
Yeah. And we have a citation for that. Even sufficient regulation can produce some of the negative features mentioned above. One example of this is the application of regression techniques, which do not allow for the generalization. High-dimensional polynomial regression leads to extreme overfitting, while chaotic systems result in even worse generalization. Good regulation is more than simply interpretability or improved efficiency. What is needed is a good world model regulator that provides a compact generative model that can be applied as an iterative but universal policy. Let's do a phase. It's not the crazy one though. Okay. So how is EGRT related to these machine learning models? Now we want to map these things to a variety of other model of this. The difference between R and S is the difference between the model of the world and the training set. We also wanted to define the regulatory aspects of machine learning and reinforcement learning in terms of world model mappings. To arrive at conclusions about world modeling, we must consider different styles of modeling. There's state of the art in the literature and connection to various natural representational systems. Is this differentiation like not the same as like biology versus artificial, but natural, like as in just not cognitive, I guess?
Yeah, maybe that shouldn't be there. Maybe it should be like just various representational, because you can have representations in nature, right? And in artificial systems. I don't want to get into that discussion either, so no one does. Let's see, yeah. So yeah, that should probably be changed.
I'll do
emoji.
I'll do this. I'll have that as a suggested change.
Okay.
Or like, yeah, the comments will make sense. Okay. In training physically for physics-inspired models, we like to predict stochastic and potentially chaotic systems. Avalanche models such as breakdown, susceptibility, and relaxation time numerically diverge as the failure threshold or avalanche event is approached. In this case, the prior information leads to non-convergent outcomes in contrast with standard gradient descent. The EGRT provides means excuse me, to escape this conundrum by allowing complex regulatory regimes. If a given model is able to capture these divergent states, maintain ergodicity, then prediction becomes possible. For non-equilibrium distributions, we require open systems that resemble Markov processes and are reconfigured according to the rate of change in entropy. Oops, sorry. And then, while explicit stimulus response links are shaped by reinforcement, generalized control in the model system is driven by more abstract control processes that can't be acquired and used independent of any one specific context. Computational RL operates on the premise of selecting between different control policies. The search for which are optimized by both the current state and the feedback signal. Together, they offer a summary of mean behavior and immediate behavioral response. Representations can further help us understand how extensive the model system must be to capture good regulation. And so I'll demonstrate this through model stitching, where stitching is enabled by convergence of the world model's representational capacity and the optimal performance characteristics. This example provides support for the notion that good models utilize similar representations of the system. Oops, still in this mode. Okay. Can I just do that? Okay, sure. Any comments or questions before we get to the next part?
I don't think so. Yeah.
So EGRT shares structures with the model training and latent spaces. EGRT structures share structures and other potential methods for constructing world models. G-flow networks allow us to sample from diverse training sets during active learning, creating flexible and open representational model. Aside from model performance on specific tasks, G-flow nets can allow us to estimate statistical distributions for unspecified variables and composite objects. As is the case with Markov processes, the structure for G-flow nets allow supergraphs to be constructed from subgraphs. These examples reveal brittleness of the EGRT. Certainly, the sentencing.
Yeah.
Is it
The
like,
brittleness.
yeah? Oh, I guess yeah. It's. Does it make sense? I mean,
What does brittleness mean, I guess?
yeah. I guess it means like it's not like suited to do that kind of a job.
Okay.
Or yeah.
Okay.
But yeah, let's see. I'll just write it.
Just like shortcomings?
Yeah, probably. Yeah, it's a better word.
Yeah, I think it's also like the compare are we basically differentiating this first sentence from G-flow networks, or is G-flow networks like supporting this, I guess?
Well, this is kind of a discussion. Well, let's see. Okay. So it's just kind of an example of something from ML model training. So although the EGRT shares structure, there's this example of G-flow nets, and then that's something that is kind of a shortcoming. So I guess that's the idea.
Okay.
So it's kind of like an exception.
Okay.
Which would probably be better up front, but yeah.
Okay. Certainly in the case of world modeling, introduction to elements is key. We can look at the GSLAM for expansion of neural representations via latent space sampling. 2, perform sensory motor integration. Yeah. GSLAM architectures expand by discovering potential loop closures, graph relaxation, and node duplications for enriching the representational model. Globally, our world model would serve as an expanding, extensible representation, while local good regulator models would serve as low-dimensional, special case models that manage feedback and reevaluation of multiple timescales. Variation and interactivity conspire to yield good representation. One definition relevant to RL is disentangling explanatory factors of variation. Another imperative of the regulations is achieving continually improved control between agent and environment. This was demonstrated by Kunze via closed-loop active learning to understand multi-process landscapes and novel materials. Continual improvement relies upon selecting for multiple potential outcomes. There should exist an RL policy that modifies selected factors without modifying others, operating as causally specific source of good regulation. Predicting avalanches, figure 1, may also require homomorphic mapping of the model to rarely observed tail events that provide sparse representation at best. Model training with a prior distribution does not help here because the structure of this exponential can only be accurately predicted from direct observation. Using algebraic operators can map to subsets of a Gaussian distribution and a model variational inference. Even the NML model training process itself requires us to understand non-IID features of a potential world model. Regularization, a method called stochastic noise injection, can introduce asymmetric exponential noise that resembles asymmetric edge.
I see.
I think this is a
Yeah.
double.
It resembles maybe something else. I have to go back and look, but.
Okay. One example of procedural learning shown in Figure 4 is not only applicable to forced adaptation and color acquisition. So-called contrastive learning techniques operate in the same manner. Contrastive learning provides negative examples to balance out positive examples of a given class, thus reinforcing, oops, I just lost my space, sorry, boundaries of category or class. Due to limitations of finding truly informative contrasts, they provide a technique for contrastive learning using hard negative examples. Clusters defined by positive samples are intentionally pushed apart by hard negative signals. This can be learned from examples or from the introduction of 1 over F or super diffusive noise. The learning, unlearning, relearning paradigm might improve the informativeness of the world model by taking advantage of representing non-IDD, IID, and expansive network structures. So rounding out this section, these world models need to embody continuous intelligence. The advantage to viewing machine learning intelligence in terms of the EGRT is that it allows for something that is not just a passive representation of data. Intelligence is not simply a camera with a finite capacity, but a dynamic system that connects different domains of knowledge. The limitations of capacity still exist, but do not necessarily limit our perspective on the world to the finite states of a Markov model or a neural network. These world models might specifically specify embodied models where there is an observer, consistent with second-order cybernetics, rather than supervision via labels. Ultimately, an artificially intelligent system may require an embodied model of the system observer to achieve sufficiently good regulation. Properties of the EGRT can interface with these models in a way that enriches the resulting world model. For example, feedback and regulation can act to influence the transformation of input data. Feed-forward can be a driver of noise, while feedback can act as a smoothing mechanism. The concept of a data stream in real time naturalistic behavior consistent with perception-action coupling is more consistent with EGRT than conventional training techniques. Continuous sampling of the world results in the presentation of new model parameters and architectural features. Sometimes these new model properties that have not been categorized by intelligence. Sometimes these new model properties that have not been categorized by intelligence.
Yeah, I don't I don't know. Maybe there's a like that is not supposed to be there, but yeah, let me. Oh, yeah, we'll see.
I think I get where it's going. I just don't know what to say. I'll just finish this paragraph before thinking about it more. Additive generalization sampling in dynamical systems allows us to generalize across attractor basins, being able to find the proper context in unseen domains. This type of approach to additive generalization phenomena allows us to better forecast extreme events, tipping points, and predict tipping points events. Like, I'm not sure we want to add this sentence here, but just like for my understanding, basically saying like this type of approach, we can forecast these events and also sort of, it's almost like I want to mention allostasis here, not in this paragraph, but like in my mind, it's like allostasis, but then what are sort of finding the line where the like where there are sort of the points, the allostatic points, but then what sort of the limitations of them too. I didn't think about it, it's better to say that. I'll come back to that.
Sure.
Okay, so we got through part 3.
Yeah.
I think this is good. We're finding like this is all, you know, it's exciting. Like I like this is fun to kind of just say, okay, this is what we're kind of seeing. I think we're finding some really nice points and a few things to maybe adjust.
Yeah.
I think that last section 3.4, that's really good. That made a lot of sense to me. What maybe didn't make sense at every point is how the previous part of the section like supported this.
Yeah.
Some of it, I just, if the connections could be made more clear.
Yeah.
I mean, I'm sure looking at the citations would help me understand. So I don't know how much more there is to say in the paper, because obviously there's a word limit, but trying to make it more explicit how the details support these general claims. Because I feel like, yeah, I have a good understanding of these general claims in 3.4.
Yeah.
Yeah, that's well said. Yeah. I think we're pretty much we're almost there. We could probably we can maybe talk about this a little bit in the next meeting too, to just like review thoughts, or like if you want to update it between now and then somewhat, or discuss things. I think we're close to finishing
Yeah.
this pass at it. Yeah. So discussion. What are the structural insights of good regulation? To better understand the structure of good regulation, we can analyze the examples from Conant. From the visualization in figure 1, we can see that R and S serve to jointly regulate the output of or Z so that target G is achieved. S regulates against S in a manner similar to generative adversarial system. And also in figure 1, R and S are presented as contributions of output Z, but in cases where R and S are from I guess it's a bidirectional, where's the suggest thing? Yeah. Can I just do that? Sure. From bidirectional presented as contribution output, we have bidirectional interaction feedback loop. R must provide the correction to S. The regulator is also subject to these entropies at different rates, which requires continual updating of the model with regard to the environment. Taking this further, two strange fellows provide a model called cybernetic convolutional architecture, which places the EGRT model system mapping into a model of suboptimality. In this case, the feedback loops provide exceptions and processes at different scales in a manner similar to GFlow networks and GSLAM. Generally, we propose a compositional approach where the system is decomposed in a set of connected subsystems, each controlled by a distinct model, closely approximates the notion of a world model. Feedback is crucial to good regulation, as feed-forward exclusive control disallows accumulation of regulatory signals. Translated to training set and learning models, quasi-temporal or sequential structure is required as an input for good regulation of an output. So, Conant points to two types of regulation that characterize discrete regulatory system, point regulation and path regulation. Excuse me. In point regulation, good regulation results from the imposition of a constancy for a scalar. The point of a thermostat, the set point of a thermostat is but one example. In terms of figure 1, Rx to minimize the entropy or fluctuation of Z, and increase chances of reaching target G. By contrast, the path regulation X to minimize the unpredictability of sequential outcomes. The entropy of a sequence time series resulting in output Z is minimized, thus increasing the chances of reaching target sequence G. We might say that path regulation is a necessary condition for point regulation. From a cybernetics perspective, this network is influenced by changes in the system, whether they be single events or phases of behavior. This provides a route to procedural learning and subsequent predictive capacity without relying on a contrived teleological mechanism. What are the limits to EGRT? To understand the challenges posed by complex systems, often non-IID contexts, we can use two types of data that may pose challenges to statistical and procedural learning, respectively sandpile avalanche frequency and the alternating between different forces and learning conditions. We introduce these examples to explore whether the regulator will develop generalized strategy to deal with constant irregular change with constant and irregular pattern change in different ways. These are considered off-policy approaches, which, in a manner similar to out of distribution data, pose challenges to good regulation shown in these examples. For using RL formulation, an agent is trained using combination of data collected by other agents of policy data, and data collects itself to learn generalizable skills like robotic walking or grasping through policy refinement. You can also map gradient descent and policy refinement to the EGRT variables described in Figure 3 and in A and Figure 5. While we do not approximate LM architectures in Figure 5, control theory has been used to analyze LM architectures in a manner similar to what we're proposing for understanding and deploying good regulation. Do we want to look at Figure 5 now?
Yeah.
Yeah, let's do that. So we have this here, and we can see it a little bit. Oh, I guess I can't look it up here. Yeah. So examples of gradient descent, A, and policy refinement, Q learning, as good regulators.
So this is just taking the like their equations for gradient descent and Q learning, and those are being taken apart here, and each like parameter or variable is being represented by a box, and then you have some like feed forward or feedback action. You can see that, and then on the right it kind of describes in the context of the equation. So the current step is the sort of the thing you're solving for the learning and gradient step, and then the thermodynamic gradient loss function. So those two pieces, and you can see on the left, those two pieces are kind of you have that feedback mechanism, and then you have Q values, which is what you're solving for in Q learning. You have cumulative rewards in the current state of action, and then a similar thing on the left where there's feedback for both of those.
Okay. I think we're here. Yeah. Another route to go to on the route to good models of changing conditions is to achieve ergodicity based on full experience with a system. Most systems involve shifting environmental conditions that characterize novel dynamical states. Models of those systems are thus non-ergodic and require a set of mean behavior that sample the global states of the system. Boltzmann statistical mechanics operates according to three assumptions. A system is partitioned into discrete states, approximate their time average probabilities, and then assume ergodicity, even if this holds true only for a small number of states. Deliberate overspecification consistent with the regulator behavior in Figure 4 may allow us to overcome this. For example, we can overspecifying only a part of the regulator's response. Is that strangely worded, or is it?
Yeah, it should be overspecify. I guess for one thing, and then
Okay.
yeah.
And then alternately represent every possible state in a training set, even when not observed or empirically unobservable. This can be understood in terms of the sandpile model. The regulator must have experience with avalanche scale events. Most common, the states over time is non-avalanche states. While oversampling non-avalanche states provides with sufficient model of equilibrium states, it is the out of equilibrium states that lead to the failure of the regulation. Map R becomes better than the territory. Sampling all possible knowledge or states allows us to recognize avalanche scale events come at the cost of time resolution as the proper temporal placement of avalanche is lost. Okay. And then this last bit here, how do we connect good regulation to intelligence? Wong proposes intelligence as a lifelong learning and adaptive process driven by embodied experience, which occurs in real time under insufficient information, open-ended, and is embedded in an ever-changing, non-repeatable world. There's several aspects of this definition when they relate to good regulation. The need for embodied experience is paramount. In addition, information in observed systems is often sparse and otherwise incomplete. The observation of the regulator are open-ended, which means the states and behaviors of the system, and even the system itself, are continually changing over time. Relatedly, the world has a unique aspect to it which deviates from the notion of optimization or even the concept of memory itself. Overall, the processes are crucial to leveraging leveraging the good regulator. In the context of AI systems, viewing training data or a series of policies as a process enables robust, resilient properties in the resulting model. Okay, I'm gonna do this. So we made it through this, and we're basically out of time. Any pressing thoughts? We can obviously comment on them more, and there's a few references I wanted to look at more on my own or whatever. But
next time we should go through the references and kind of look at what they are, because there are a lot of really good references in here. But
yeah, I would actually like to do that. I didn't know if people were going to want to do that, but I would like to do that.
Yeah, I would like to do that too. I'll try to do some of that on my own time too before we meet
Do-
next.
Do we want to pick do you want to just basically go through top to bottom references, or pick any out to?
Well, I mean, we can go top to bottom, and we can pick some out beforehand and then highlight them.
Okay.
Say, okay, this one is good.
Okay. All right. I mean, that's I assume that's plenty for today. We can do that. Is there anything you want to a reference people want to specifically mention to try to read before the next meeting or something? We can mention that in Slack perhaps. But
Okay.
Otherwise, I'll say good stuff for today, and we can we can cover this next week probably in Condition Futures. I may have some other stuff there, but I'm happy to kind of just do more intense focus on this, just because there's a lot of good stuff here. So yeah, it's good. All right. I'll talk to you guys next time. Thank you.
All right. See you later. Thank you.
See you soon.
Talk to you soon.